Similarly, just as Nicholas Copernicus presented the heliocentric model, another dazzling correction in how we might learn about the universe's formation has emerged. This launched a debate known as the emergence of cosmology. This emergence is set apart by critical disparities in our estimations and comprehension of the universe's crucial properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has mentioned that the discovery of the James Webb Space Telescope, JWST, has halted this discussion with an image that defies material science. So, what precisely is this crisis, and how does the James Webb Space Telescope contribute to it? Well, saying it contributes is a bit of an overstatement. It is more of an ongoing survey. The crisis refers to a challenge in our understanding of the universe, particularly regarding its age and size, which are connected by a significant margin of uncertainty. The introduction of the JWST has been pivotal in this context. Before this advancement, our ability to observe the early universe was limited. However, with the JWST's enhanced capabilities, astronomers can now investigate distant galaxies, providing new perspectives on the universe and allowing us to reassess past conceptions. This progress enables us to look further back in time, closer to the Big Bang, and observe galaxies as they were forming. These observations provide crucial data that can either support or challenge our current cosmological models. To understand this crisis in detail, we must consider the standard model of cosmology, known as the hot inflationary Big Bang model or the lambda cold dark matter, CDM, model. This model has been remarkably successful in explaining various aspects of the universe, from gravitational lensing to the structure of the cosmic web and the evolution of galaxies. The CDM model states that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the universe's accelerated expansion. However, every groundbreaking observation, particularly those made with advanced instruments like the JWST, raises the possibility that our current model may be incomplete or in need of revision. The CDM model makes explicit predictions about the properties and behavior of galaxies at different epochs in cosmic history. For example, it predicts that galaxies in the distant past should be less compact, less evolved, containing fewer heavy elements. This is because heavier elements form in stars and are distributed through processes like supernova explosions, which take time to take effect. The Standard Model of Cosmology also predicts how galaxies move within clusters and how the cosmic microwave background, CMB, should appear as we look further back in time. According to this model, galaxies at extreme distances should be smaller, less evolved, poorer in heavy elements. At some point, this should lead to an era in the universe without stars or galaxies. However, researchers have found contradictory evidence that challenges these expectations, leading to a crisis in cosmology. The crisis in cosmology. This crisis revolves around uncertainty regarding the age of the universe. Different measurement methods yield varying results, leaving cosmologists struggling to reconcile these discrepancies. To address this issue, researchers use several techniques to estimate the universe's age. One key method involves studying cosmic background radiation, which helps trace the history of cosmic expansion. Scientists use mathematical models, such as the Friedmann equations, based on Einstein's general relativity, to determine the universe's expansion rate and, consequently, its age. The CMB, a remnant of the early universe, is crucial for these calculations. Detailed maps of the CMB, such as those provided by the Planck satellite, a European Space Agency mission, offer valuable insights into the universe's composition. However, these maps lack direct data on dark energy, a critical component of the universe. Despite this limitation, researchers can still use the Friedmann equations and additional observations to estimate the universe's expansion rate at different times and determine its overall age. Another method, supernova observations. Another way to measure the universe's age involves observing exploding stars, specifically type Ia supernovae. These supernovae serve as standard candles because they have a well-known intrinsic brightness. By comparing their known brightness to their observed luminosity, astronomers can determine their distances and, therefore, measure the universe's expansion rate at various times. This method was instrumental in the 1990s discovery of dark energy, which is now a crucial factor in cosmological calculations. It is also particularly useful for determining the Hubble constant, a measure of the universe's expansion rate, which, ironically, is not truly constant. The Hubble constant is fundamental to understanding the universe's expansion since the Big Bang, which occurred approximately 13.8 billion years ago. Observations show that the universe has been expanding consistently. NASA has noted that the implications of this expansion rate are profound. If the expansion is slowing down, it suggests the influence of an unknown force, possibly dark matter, affecting this process. If the expansion is accelerating, it indicates that dark energy is driving the universe's rapid growth. The expansion debate and its implications. In January 2023, new data from the James Webb Space Telescope, JWST, deepened the debate on the universe's expansion. Researchers had already been grappling with discrepancies between different measurements of the Hubble constant, with results from the CMB, via Planck, differing from those obtained using supernovae. This inconsistency, often referred to as the Hubble tension, has fueled speculation that our current cosmological models might require modification. The JWST's observations have introduced even more uncertainty. By detecting galaxies that appear too massive, too evolved, and too structured for their supposed cosmic age, the JWST challenges the CDM model's timeline. Some of these distant galaxies, observed from when the universe was only 200 to 300 million years old, already exhibit features that should have taken billions of years to form. This finding raises fundamental questions. Are our measurements of cosmic expansion flawed? Could dark matter and dark energy behave differently than we expect? Is there a missing component in our understanding of early galaxy formation? These unresolved questions are central to the crisis in cosmology and have led some scientists to propose alternative models. Potential explanations for the cosmological crisis. 1. Revised dark matter theories. Some cosmologists suggest that dark matter may interact with itself or with regular matter in unexpected ways, influencing the formation of galaxies more rapidly than anticipated. 2. Modified theories of gravity. Alternative models of gravity, such as modified Newtonian dynamics, MOND, or extensions to Einstein's general relativity, attempt to explain these anomalies without invoking dark matter. 3. New physics beyond the standard model. Some physicists speculate that undiscovered particles or forces could be altering the universe's expansion, potentially linking quantum mechanics with cosmology. 4. Flaws in the standard model's assumptions. If our assumptions about the early universe's conditions are incorrect, such as the density of matter or the rate of expansion, our models may need significant revision. How the JWST is reshaping cosmology. The JWST is not only detecting galaxies at unprecedented distances but also providing spectroscopic data that reveals their compositions. By analyzing the light emitted from these early galaxies, astronomers can determine the abundance of elements such as hydrogen, helium, and heavier metals, shedding light on the processes of early star formation. Additionally, JWST's ability to observe infrared light allows it to penetrate cosmic dust, revealing structures that were previously hidden. This could help resolve some of the mysteries surrounding galaxy formation and evolution. The future of cosmology. The next decade will be crucial in resolving the Hubble tension and refining our understanding of the universe. Future missions, such as the Nancy Grace Roman Space Telescope and ground-based observatories like the Extremely Large Telescope, ELT, will provide additional data to test competing theories. Meanwhile, the CDM model remains the best explanation for most cosmic phenomena, but if JWST's observations continue to challenge its predictions, a paradigm shift in cosmology may be inevitable. Final thoughts. The crisis in cosmology is not necessarily a setback. It could be a breakthrough moment that leads to new discoveries about the nature of the universe. Just as Copernicus's heliocentric model revolutionized astronomy, the observations made by the James Webb Space Telescope may be the catalyst for the next major leap in our understanding of the cosmos. One thing is certain. The universe is far more complex than we ever imagined, and we are only just beginning to uncover its deepest secrets. In 2018, researchers made a discovery. Despite the fact that some telescopes demonstrated that the rate of expansion of the universe changed, the Hubble Space Telescope's observations measured a faster expansion in the nearby universe, while the Planck telescope recorded slightly lower measurements of expansion in more distant parts of the universe. This difference in measurement highlights the immense size of the universe and reminds us of the pioneering work done by Edwin Hubble. In 1929, Hubble first proposed the expansion rate of the universe. His observations of distant galaxies revealed that they were moving away from us, demonstrating that the universe is growing. This discovery became one of the foundational principles of modern cosmology. The expansion of the universe is considered to be independent of any local region. No matter where you are, you would observe the same phenomenon at the same speed, known as the Hubble expansion rate. Initial calculations were based on limited data. However, with technological advances, such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Different cosmic microwave background, CMB, readings are taken by telescopes to calculate the Hubble constant, though this method has limitations due to the availability of supernovae for distant observations, which help us study the universe. Since the discovery of dark energy in the 20th century, research has been stumped by inconsistencies between different approaches to measuring the age and expansion rate of the universe. As measurement technology becomes more accurate, smaller variations arise, driven by advancements in more sophisticated systems. This progress, however, raises more questions than it provides definitive answers. Although the differences in measurements are minor, just 10 to 20 million years between estimates, given that the universe is approximately 13.77 billion years old, it still warrants careful investigation. One potential explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most precise measurements ever achieved, the CMB has been extensively tested since its launch in 2009 to validate its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may fluctuate over time and be linked to dark energy or another unknown factor. This hypothesis has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Settling this uncertainty in supernova models could help resolve the disparity in measurements. This cosmology emergency has been further exacerbated by the discoveries of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, JWST has discovered objects in the universe that challenge our current understanding. This suggests that our scientific knowledge requires a complete update. However, the problem is that we have no idea where to begin in comprehending the extent of this scientific revolution. Let's take a look at the universe's beginnings. Around 1 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially as soon as 50 to 100 million years later. However, these events should have been relatively rare. What we don't yet understand is how common galaxies became at later times, particularly between 400 million years after the Big Bang and beyond. Ongoing JWST images reveal galaxies much more distant, and therefore older, than the standard cosmological model predicts. This disparity suggests that our model needs a major update. The discovery that the universe is expanding, based on galaxies, is a major development. JWST images show galaxies that formed significantly earlier than anticipated by current cosmological models, triggering a crisis in the field. This issue is closely related to galaxy formation and redshift, a common measurement in cosmology. According to the standard model, hydrogen began to appear 400,000 years after the Big Bang, when protons and electrons combined, leading to hydrogen recombination. This process transformed the universe into a vast soup of hydrogen atoms, with a small amount of helium and some background radiation. Gravity then acted on small fluctuations in this hydrogen gas, slowly pulling them together to form the first stars. These early stars, composed mostly of hydrogen and helium, engaged in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played an essential role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen. But as time passed, heavier elements produced in the cores of stars were introduced. This process led to the formation of galaxies containing not just hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential for life. As the universe evolved, these newly formed galaxies began to cluster together, influenced by the gravitational pull of dark matter. Over billions of years, these clusters merged and formed the large-scale structures we observe today, including galaxy superclusters and vast cosmic filaments stretching across the observable universe. Despite our growing understanding of cosmic evolution, many mysteries remain. One of the most pressing questions concerns dark matter and dark energy, which together make up approximately 95% of the universe's total mass energy content. Dark matter, although invisible, exerts a gravitational influence on galaxies, preventing them from flying apart as they rotate. However, its true nature remains unknown, with leading theories suggesting it may consist of weakly interacting massive particles, WIMPs, or actions. Dark energy, on the other hand, is even more enigmatic. It is believed to be responsible for the accelerated expansion of the universe, as first observed in the late 1990s through studies of distant supernovae. The exact mechanism driving this expansion is still unclear, with some theories proposing modifications to Einstein's general theory of relativity or the existence of a new fundamental force. The James Webb Space Telescope, JWST, has provided new insights into these cosmic puzzles. By capturing high-resolution images of ancient galaxies, JWST has revealed that some galaxies formed much earlier than previously expected. This discovery challenges our current models of galaxy formation and raises fundamental questions about the conditions in the early universe. If galaxies emerged sooner than anticipated, it could suggest that our understanding of star formation, cosmic inflation, or even the behavior of dark matter needs revision. One potential explanation is that the first generation of stars, known as population 3 stars, may have formed more efficiently than previously thought. These stars, composed almost entirely of hydrogen and helium, were significantly larger and hotter than modern stars, rapidly synthesizing heavier elements and influencing the formation of subsequent generations of stars and galaxies. However, direct observations of population 3 stars remain elusive, and their existence is still theoretical. Another significant challenge in modern cosmology is the Hubble tension, a discrepancy between different measurements of the universe's expansion rate. Observations from the cosmic microwave background, CMB, suggest a slower expansion, while direct measurements of galaxies and supernovae indicate a faster rate. This inconsistency has led some scientists to propose new physics beyond the standard model, such as variations in dark energy over time or previously unknown interactions between fundamental particles. As telescopes like JWST and upcoming observatories such as the Nancy Grace Roman Space Telescope continue to refine our measurements, we may soon gain a clearer picture of these cosmic mysteries. Future observations will help determine whether the discrepancies in our models stem from measurement errors, missing physics, or an entirely new paradigm of cosmology. Ultimately, the universe continues to surprise us, revealing new layers of complexity with each technological advancement. While we have come a long way since Edwin Hubble's pioneering work in the 1920s, the quest to understand the cosmos is far from over. The next decade of astronomical research promises to bring us closer to answering some of the most profound questions about our universe's origins, structure, and ultimate fate.